Good morning, everyone. Hope you're all doing well. So we like killed it last lecture. So we're gonna keep moving through. Hopefully give ourselves a day off next week. I want us to do one more example of a Lewis dot structure. It'll be off of your lab, so you can save this and use it. I want the Lewis dot structure, I want the electron geometry, and I want the molecular geometry. So let me share my screen with you. We got someone. Morning. Okay. Come on. So all that fun stuff I want you to do for Cl2O. So we call this what? Dichlorine monoxide. So I want you to do the Lewis dot structure, the electron geometry, and the molecular geometry. Sometimes the electron geometry is called the overall geometry. Just know if you see that on your lab, it's saying overall geometry. That's what it's talking about. Give you another minute. Okay, so working on this one. Hopefully you got something that's similar to water, H2O, at least in like the geometry sense. So let's go over it. The number of electrons we get to play around with. Chlorine is 7 times 2 plus another 6. So 14, 20. 20 electrons. Okay. We want to make this thing balanced. So I'm going to put the oxygen in the center and the chlorines on the side. Next step, stick it together. Okay. Then we go outside to inside. So make the outside happy. Chlorine needs an additional 6 to complete its octet. So does this chlorine. All right, I have 16 electrons on the board. I need 20. So I'm not going to make a double bond or anything like that. I'm going to just add the other 2 electrons. So 2 there and 2 there. If you put 2 here and 2 here, that's fine too. Just sort of like kind of couple them together. So this is what the Lewis dot structure should look like. The overall geometry takes into account every electron group. So as far as the electron groups are concerned, and this is only the electron groups in the central atom. So I've got 1 here, and here, 2, 3, 4. 4 electron groups, or sometimes they're called domains. So 4 electron domains. Okay. So tetrahedral. Now the molecular geometry, a lot of times people will jump into this and go, oh, it's linear. See, it's in a straight line. But it's not linear because these 2 electron groups here are affecting the other 2. So think of your tetrahedral pyramid of 1, 2, 3, 4 here. Okay. So this is supposed to be a 3-dimensional pyramid. And we have a chlorine over here and a chlorine over here, but we're missing these 2 here. This is a bent structure. All right, 3-dimensional, so it'd be bent, or we call it V-shaped, bent or V-shaped. You guys feel good with that? Throw in the comments if not, if anything in that didn't make sense. You should get a good amount of practice on the lab, but we've gone over quite a few on the lab as well. So keep your notes by when you're doing the lab. Okay, let's finish up this chapter talking about oil and water and why they don't mix, and this whole idea of electronegativity and yada yada. How do you know electron groups? How do I know how many electron groups I have? Okay, so you go to look at the central atom. One question on this, yeah. You look at the central atom and you see how many areas there are of like electrons. You don't go off of a single electron. Usually the electrons are paired together. So this lone pair here would be classified as 1 electron group. This lone pair here would be classified as 1 electron group. And then each of these bonds is 1 electron group. It's an area where you have an electron cluster. And the reason that you want to count those up is because those electron clusters want to consistently get as far away from each other as they can. So if there's 4 of those groups, the farthest they can get away is tetrahedral. If there's 3 of those groups, the farthest they can get away, it's a little farther, it's trigonal planar. If it's 2 groups, it's linear. As far as what we classify as an electron group or an electron domain, 1 lone pair Okay, not two, so I wouldn't count both of these as one. One here and one here. One single bond. Okay, so this is classified as one electron group. One double bond. A double bond is not considered two electron groups. A double bond is considered a single electron group because the double bond is sealed off on both sides. So that double bond can't split open to like spread itself out. It's a unit. Also, one triple bond is classified as one. All of these things are considered one electron group, one electron group. Does that make sense, Seth? You just throw it in the notes, yay, nay. Okay, perfect. So electronegativity and polarity, and why oil and water don't mix. So here's a jar or a glass, and we've got water sitting on the bottom and the oil sitting on the top. The oil sitting on the top because it's less dense. Why don't they mix? Same thing with like your, vinegar, oil, salad dressing. You can shake it as much as you want and it'll disperse it, but it's never going to like fully mix. It'll always separate. There's, why is this the case? There's something about water molecules that cause water molecules to bunch together. So the water molecules like to hang out with each other and they kind of expel or push the oil out. Why is that the case? Well, let's look at this molecule right here. So we've got a single water molecule. There's hydrogen and there's oxygen. This is, they're sharing this electron group, right? So we've got this bond here that's being shared, but it's not being shared equally, okay? Because these are different types of atoms. And depending on the atom you're looking at, some atoms are greedier for electrons. Oxygen is so greedy. It loves the electrons. So it's going to keep the electrons closer to it than the hydrogen. Right? So the electrons will sort of kind of shift their way closer to the oxygen. The hydrogen is still getting access to them, but not as much as the oxygen is. The ability of an element to attract an electron within a covalent bond is known as its electronegativity. So if something has a high electronegativity, it's greedy for electrons. Low electronegativity doesn't care quite as much. So if you have an imbalance in your electronegativity, you get what's known as a dipole moment, D-I-P-O-L-E moment. Sometimes it's symbolized with a little like delta symbol. The positive delta symbol is on the side where the electron isn't quite as much. The negative delta is on the side where the electron likes to hang out more. So here I've got oxygen and here I've got hydrogen and all these like random pink dots. This is a probability cloud of where we would expect the electron to be. We actually would expect the electrons to hang out more around the oxygen because oxygen has a higher electronegativity, it is greedier. So when you have these, this imbalance in sharing or this dipole moment, we get what's known as a polar bond. Okay, dipole moment, also sometimes called a polar bond. Polar bond. Polar because it has like poles to it, right? So, or sometimes it's called a polar covalent bond. So a polar covalent bond is when the electrons are shared, but they're not shared equally. How large the dipole moment is, or that asymmetry, is dependent on the electronegativity difference between the two elements. So if the two elements have a really similar electronegativity, they won't have a very strong dipole moment. They won't be a strong polar covalent bond. If they have a large difference, then we will have a larger polar covalent bond. So the values of electronegativity, it's assigned using a relative scale. So these numbers don't like mean anything. They don't have a unit. They're just all in reference to fluorine because fluorine has the highest electronegativity. So they kind of arbitrarily gave fluorine the value of 4. All the other values go down from there. So this is the highest electronegativity. So if you want to put this on your periodic chart, and this doesn't include the noble gases because they don't want electrons. So fluorine has the highest electronegativity and it gets lower as you move down and to the left. Remember, what is electronegativity? It's something's ability to pull or attract an electron. These guys, they barely want their electrons anyway, so they don't have a very high electronegativity. Now, to determine how strong the polar bond is going to be, you can subtract these two. So let's say we're combining fluorine and oxygen. It's a bond of fluorine and oxygen. Well, the difference in those numbers, it would be 4 minus 3.5 or a value of 0.5. Okay. What if we were combining chlorine and nitrogen? And I don't expect you to have electronegativity numbers memorized. So let's say we were combining chlorine and nitrogen. Okay, well, chlorine has a value of 3. Nitrogen also has a value of 3, so their difference is actually 0. They actually share the electrons pretty equally. And there's a chart where you kind of get the value where you can cut this off. So I'm going to move forward to this slide. So here are the cutoff points for the different types of bonds. If you have a difference in electronegativity of 0.4 or less, we just call that a pure nonpolar covalent bond. That means the electrons are sharing equally. You see how the little bubbles are the same? It's because the electron cloud is balanced or equal throughout. This happens a lot of times with like diatomics where you have chlorine and chlorine. They're going to share the electrons equally. There's not going to be any sort of polar quality. So we call it nonpolar. What happens when we have a value difference of anywhere between 0.4 and 2 with our electronegativity? This is that sweet spot where we get a polar covalent bond, where the electrons are still being shared, but they're not being shared equally. One partner is greedier than the other, so it's going to hold the electrons a little bit closer. And then there is another situation where the difference can be so great in the electronegativity. If it's greater than 2, all the way up to like 3.3, this is a situation where we get an ionic bond or a metal and a non-metal, like sodium and chlorine. Let's look at those numbers. Sodium over here is 0.9, chlorine over here is 3. That's such a huge difference in electronegativity. This is so greedy for the electron, and this isn't greedy at all, that it just transfers the electron. And when we transfer an electron, what do we get? An ionic bond. It's a different type of bond. So, yeah, so we want to be able to determine like if the bond itself is polar or nonpolar, or or ionic. Now, just because you have, sorry about that, just because you have a polar bond in a molecule does not always mean that the whole molecule itself is polar. A polar molecule, so polar bond is between 2 adjacent atoms. A polar molecule is when all the polar bonds add together, they don't cancel each other out to form this sort of net balance dipole moment. So let's look at this right here, carbon dioxide. The bond between carbon and oxygen, this bond is polar. Because carbon and oxygen are different nonmetals, they're going to share the electrons slightly differently. But, so you can even, sometimes they draw them as vectors, like little arrows, pointing in the direction where the electrons like to hang. So the bond is polar, but there's a second bond over here that's also polar in the equal and opposite direction. So it's creating a overall net balance to the molecule. It's kind of like if you've got a tug of war, right? There's 2 ropes and it's an equal strength pull from both sides. So the molecule itself is non-polar. polar bond, non-polar molecule when all of the things add up and balance each other out. Does that always happen? No. Let's look at a situation where that doesn't happen. So let's look at water. Water is not, shares the electrons asymmetrically, and they didn't draw the lone pair, and I don't know why. I'm going to put them here. So there's 2 lone pairs of electrons. Right, you guys remember that for water? We've got the 2 lone pairs here. So think about it as almost like there's 4 ropes coming off of this, but 2 people just decided not to show up. So these 2 people are in position, they're pulling, and there's no one to pull back in an equal and opposite direction. So this becomes imbalanced. Now, if that concept is tricky for you, one thing that you can go off of is the lone polar bear. Write that. The lone polar bear, which means if you have lone pairs on the central atom, it's a polar molecule. Okay, that will get you through 98% of classifying a molecule as polar or non. If it has a lone pair, it means somebody didn't show up to the tug of war, it's imbalanced. So let's go back to that structure that we looked at earlier in class. Right here. This Cl2O, let me just redraw it. It's oxygen, chlorine. So is the bond between chlorine and oxygen polar? Yes. Anytime it's 2 nonmetals that aren't sharing the electrons equally, it's polar. But the real question is it a polar molecule? I don't know why I want to keep saying polar molecule. Yes, no. So you can, again, think of this as a tug of war, and there's 4 ropes. How many people showed up to the tug of war? Just 2 of them. These 2 ropes are limp. There isn't anybody helping to pull on those, so it's imbalanced. Or you can think, hey, there's some lone pairs on the central atom, the lone polar bear, it's polar, yes. Let's look at methane, which we did the other day, but methane has this structure, CH4, so carbon in the center, hydrogens on the side, stuck together. It looks something like this. What is its electron geometry? It's tetrahedral. What is its molecular geometry? It's also tetrahedral. Do you see any lone pairs? No, so same. All right, polar. I'm going to put polar bond and then polar molecule, because sometimes people get those things mixed up. So polar bond, yes, no. Polar molecule, yes, no. So let's take a look. Is the bond between carbon and hydrogen polar? Yeah, they're 2 nonmetals. They're not sharing the electrons equally. Carbon is going to be greedier than hydrogen. So the bond is polar. The bond is usually polar, unless it's like chlorine bonded to chlorine. Something like that would be nonpolar. But if it's 2 different things, it's going to be polar. Now, is the molecule as a whole polar? Well, look at how many electron groups you have. 4 electron groups. Did everybody show up for that tug of war battle? They did. So they're all pulling equal and opposite. So it's balanced, nonpolar. Okay? Or You could say, hey, do I have any lone pairs on the central atom? No, so we're nonpolar. So in your lab, you do have to classify whether the molecules are polar or nonpolar. The lone polar bear should get you through most of it. Questions on identifying a polar molecule or a polar bond? So how does this relate to soap? Well, we haven't even talked about soap, but how does this relate to water and oil, and then hence soap? Okay, so here's some polar, nonpolar stuff. So why oil and water don't mix? The reason is because water is a polar molecule, right? It has those two lone pairs of electrons, whereas oil is generally composed of nonpolar molecules. Now, polar molecules have a dipole moment in them. They have a side to them that's sort of positive and a side to them that's sort of negative, right? So oxygen bonded to hydrogen, and then the two lone pairs. So the side where the oxygen is over here, this tends to be a This tends to be a negatively charged area. The hydrogens tend to be a positively charged area. So this allows the water to stick to itself because the positive hydrogen on one water will stick to the negative oxygen on an adjacent water. And they kind of grip to each other. Water has surface tension to it, right? It can kind of cling to itself. It bubbles up like that. We're getting this attraction between adjacent water molecules. So it's, these guys want to clump together. The nonpolar oil, it's not that it like repels the oil, it just isn't interested in the oil. This thing just kind of, the water just kind of wants to gravitate to itself. Like if you had a container and you filled it with a mixture of sand and small flecks of magnets, what would happen? All the magnets eventually would clump together and it would push the sand out because the sand doesn't have that magnetic quality to it or that sticky quality. The water is doing the same thing. It's got a polar quality that clumps it together and repels all the oil out. So looks something like this, right? All those little water molecules are gravitating towards each other. They have a magnet here, right? The south and the north side of the magnet, or the hydrogen and the oxygen of adjacent water molecules stick together. So that's why if you've ever tried to wash your oil off of your hands with water, it's not going to work because the water isn't going to combine with the oil and strip it away. So what do you have to do to get oil off of your hands? What is that key thing that you need? You need soap, okay? So soap is so cool. It's such a cool thing. It's a molecule, really, really long molecule, and most of the molecule is nonpolar. So it's got this really long, balanced, nonpolar tail. That nonpolar part of it is able to attract the grease or the oil. On the other side, though, we have this polar head. So there's, usually you make soap through a process called saponification. You take some sort of fat, whether it's animal or plant, and you use lye and you convert it by pretty much ripping part of it off and sticking a polar head at the end of it. And so that's what gives it its soap-like qualities. So the polar head, or this sort of unbalanced, like wonky side, attracts the water. So now the soap is acting like a bridge where the nonpolar tail is sticking to the oil, the polar head is sticking to the water, and you're able to, you know, grab the grease or the oil off of, well, this side would grab the grease or the oil off of your body, and then this side tags along on the water and runs down the drain. So you have soap. So know a simple explanation for how soap works. Okay. And that is it for chapter 10. I don't know what that's about. So your test is going to be open on Sunday and it will close on Tuesday because of the holiday. Make sure you get the test done by Tuesday, but we'll see each other on Tuesday. So I'll definitely badger you all to get that done. It will cover chapters 5, which was naming and nomenclature, chapter 9, which was all the electron configuration stuff, and chapter 10, which was all this Lewis dot structure and three-dimensional shapes. So we're going to move forward to chapter 6. Chapter 6 is not on this next test. But if I was to say what is the most challenging part of the course, I would say it's the next 3 lectures. Chapter 6, chapter 7, and chapter 8. It's a lot of math. So if you don't have a calculator, grab one. Andrea is asking, for the lab, do we do all parts of each example, like the number of bonding domains on the central atom? Yeah, so the number of bonding domains, that's the number of electron domains, okay? If it's a bonding domain, it means it's a domain that is connected to another atom. The VSEPR formula, you don't have to do the VSEPR formula. If you are interested in the VSEPR, I won't test you on the VSEPR formula. If you're interested on it, there is in the last page of that lab, it talks about the VSEPR setup. It's just another way to describe kind of what we've already talked about, but I'm not super anal about that. So yeah, if you just want to ditch the VSEPR formula part, you can, but the rest of it I do want you to do. So goodbye, chapter 10. Hello, chapter 6. Okay, so chapter 6 is all about chemical compositions, calculating chemical compositions, calculating amounts of things. Yeah. This chapter is a long chapter. There's a lot of stuff in it. That's why I wanted to get to some of it this week so that we can break it up. All right, so in the beginning it says, hey, how much sodium? Sodium is an important dietary mineral that we eat in our food. The way we consume sodium is primarily through sodium chloride. We don't eat sodium metal. That would not be very appetizing. Instead, we digest it using salt. Sodium is super important in the body. It helps to regulate fluids, but there is a balance. So you don't want to eat too much salt. There's kind of a nice window for each individual. The FDA recommends that you consume less than 2.4 grams or 2,400 milligrams of sodium in a day. So 2.4 grams of sodium. Now that does not mean that you need to eat 2.4 grams of salt, because this is a measurement of how much sodium we need, but it's involved within this whole compound sodium chloride. So it's like, well, how much salt do we get to eat? If I need 2.4 grams of sodium, how much salt can I have? That is a process that we're going to figure out how to do. The masses of sodium and chlorine are different. So the relationship between the masses of sodium and chlorine are not specified in the chemical formula alone. So when I say NaCl, I'm not saying, hey, 1 gram of sodium for every 1 gram of chlorine, because this is a lighter molecule than this one, or this is a lighter atom than this one. So we have to do some more maneuvering. And if you're not into math, you may think it's like trickery or witchcraft, but it's not. So the information in a chemical formula, along with what are called the atomic and formula masses, can be used to calculate the amount of the individual element. So why would we want to calculate the amount of an individual element within a compound? Let's say we wanted to know how much iron is in this iron ore. So, we're excavating iron ore, which is iron and oxygen and probably some other stuff, but we don't care about the other stuff. We just want the iron. We'd want to calculate the iron. If we wanted to calculate how much chlorine is in this chlorofluorocarbon, right, these hunkier molecules, we could actually go ahead and calculate using some pretty basic chem math how much chlorine is in that. So in order to do that, we got to do some basic stuff. Counting by weighing. So the real life example that they use is nails, or measuring nails by the pound. So if you've ever gone to like a hardware store where they had free nails, not free, but like they were loose. The way that they measure out how many nails you need, they don't go and count every nail. If you're building a house, they're not going to count every nail that you need for that house. What they're going to do is throw a big hunk of them on a scale. And then they know that, you know, there's 3.4 pounds of these nails. They know that like a pound of nails is equivalent to like 50 nails or something. And they do a rough calculation, right? So they count the number of nails by weighing them. The same thing happens when we're looking at atoms. There's so many atoms that you're not going to sit there and count all the atoms. Instead, you're going to weigh the material and you're going to know that there's a relationship between the weight and the number of atoms. So here's a little calculation with the nails. A customer buys 2.6 pounds of medium-sized nails, and a dozen of these nails weighs roughly 0.15 pounds. How many nails did the customer buy? So we're going back to conversion factors and those sorts of equality relationships. So in this, we've got two things. It says a customer buys, well, this is the given piece of information. We have 2.6 nails. It says a dozen nails weighs 0.150 pounds. So that's our first conversion, right? 1 dozen nails equals 0.15 pounds. Our second relationship, the question isn't asking you for the number of dozens, it's actually asking you for how many nails. So we need the relationship between a dozen and individual nails, which is 1 dozen of any nails equals 12 nails. So we can convert pounds, 2.6 pounds, we can convert that into the number of nails by using these conversion factors. The first conversion factor tells us a relationship between pound and dozen nails. We know for every 0.15 pounds, we get a dozen nails. We set that up here and the pounds of nails will cancel. Then we use the second relationship that says for every 12 nails, we get a dozen. So we put the dozen on the bottom because we want them to cancel. This is dimensional analysis like we've done earlier in class with conversion factors. We know that we'll get 12 nails. So you want the units to cancel and we end up with 208 nails. Now in the hardware shop, they already kind of have that direct relationship. So if you say, hey, I need 208 nails, they're gonna say, okay, well, you need about 2.6 pounds. You might get a little more or a little less, depending on the accuracy. But there's a way to count using weight. So counting by weighing when it comes to atoms. With atoms, we must use their mass as a way to count them. Their atoms are just too small to sit there and try and count individually. Even if you could see atoms and you could count them for 24 hours a day for as long as you lived, you could barely begin to count the number of atoms in something as small as a grain of sand. Okay, you just don't have enough time on this earth. And I'm sure you don't have the patience either. So we are gonna weigh it. With nails, we used a dozen as a convenient number in our conversions, right? So we said, hey, 0.126 pounds equals a dozen nails. Well, a dozen isn't going to cut it in chemistry because what is a dozen? A dozen is equal to 12. How many atoms are there? Oh my gosh, there's so many atoms. We need a dozen on steroids. We need something that is going to represent a whole lot of something. So what we have is what's sometimes called the chemist's dozen, or it's called the mole. M-O-L-E, M-O-L-E. And the mole is 1 mole of anything is equal to 6.022 times 10 to the 23rd. Of those individual amounts. And the mole seems to, like, people get confused and they get freaked out about it. Well, let's do some simple concept stuff here. 1 dozen eggs is equivalent to how many eggs? 12 eggs. Okay, that you feel comfortable with, right? What about 1 mole of eggs? 1 mole of eggs would be 6.022 times 10 to the 23rd eggs. That's a lot. That's probably more eggs than have ever existed in the entire history of chickenry. What about 1 dozen carbon atoms? That's equivalent to 12 carbon atoms. Probably not a number that we'd use very often, 12 carbon atoms, unless we were using like some sort of carbon nanotube that was only like 12 carbons thick, but probably not. Okay, that's really, really an almost insignificant amount of carbons. What if I said I had 1 mole of carbon? That's equivalent to 6.022 times 10 to the 23rd carbon atoms. What if I said I had 1 mole of sulfur? A mole of this and a mole of this are different, right? This is a mole of carbon. This is a mole of sulfur. It's still 6.022 times 10 to the 23rd, but it's talking about sulfur atoms as opposed to carbon atoms. Right? Like a dozen eggs and a dozen people, not talking about the same thing. There are 12 of them, but they are definitely not the same thing. These are not the same thing. Right? What if I said I had a mole of water? 1 mole of water, H2O, is equivalent to 6.022 times 10 to the 23rd water molecules. It's starting to make sense? So that's a mole. That's how it goes. On the formula sheet that we have available for you in Moodle, this number is on there. You will probably end up memorizing it though, because we just use it so much. So Avogadro's number. Here's another example. 1 mole of marbles corresponds to 6.022 times 10 to the 23rd marbles. 1 mole of sand grains corresponds to 6.022 times 10 to the 23rd sand grains, so on and so on. Sometimes you might see the number as 6.02 times 10 to the 23rd. That's okay. I usually use both 2's. Some people don't. So if you're wondering, well, what is a mole of like something? Like, is this like a whole lot? Because it seems like if I have a mole of iron or I have a mole of carbon, that's a lot of atoms, right? It's actually not as much as you think. It's kind of the amount you would expect to see in an everyday, like something you could put in your hand object. So a mole of copper, which contains, mind blowing here, 6.022 times 10 to the 23rd atoms of copper, is roughly 22 pennies. Oh my gosh, so much, right? There's so many atoms. That's why we need this chemist dozen. 1 mole of helium, again, the 6.022 times 10 to the 23rd helium atoms, takes up about 2 balloons. So we're talking like everyday amount. So when I say, hey, I've got a mole of platinum, we're not talking about something that's as big as the universe or as small as like a cell. We're talking about something I could hold in my hand. Why is the mole the mole? Why is it 6.022 times 10 to the 23rd? The numerical value of the mole is defined or is equal to the number of atoms that you would get in exactly 12 grams of pure carbon-12. So pure carbon-12 being 6 protons and 6 neutrons. This relationship establishes a connection between the mass or the grams of the carbon and the number of atoms. This will in turn allow us to count atoms by weighing them. We will get there. Let's first just do some basic conversions using the mole ratio. So we'll look at this one together and then I'll give you guys one. So say we're converting moles to the number of atoms. So convert 3.5 moles of helium to the number of helium atoms. So your given piece of information is that you have 3.5 moles of helium. We want to find the number of helium atoms. We need to use Avogadro's number. That's our relationship. Moles to atoms. 1 mole of helium always weighs always is equivalent to 6.022 times 10 to the 23rd helium atoms. That is the relationship. So we're going to set it up in dimensional analysis with our given information to begin with, which is the 3.5 moles of helium. That's coming right here. That's what it was initially talking about. We use our relationship and we set it up in such a way that the mole will cancel, right? I want to get rid of the mole. I want to move into helium atoms. Are you guys seeing how this is sort of just a conversion factor, but your conversion is a new conversion that you haven't heard of probably until today. So the moles will cancel and you'll be left with helium atoms, and we get 2.1 times 10 to the 24 helium atoms. We would expect to have a lot of atoms. 2 sig figs here, so we go with 2 sig figs here. So I'm gonna have you guys do one of those. Given, and let's make a little flow chart. So we'll start with moles in the middle. And then let's put atoms over here. And let's put a little arrow between, and let's put Avo's number. So anytime I want to convert between moles and atoms, or atoms and moles, I'm going to use Avogadro's number, which is the 1 mole equals 6.0221. Mole of anything is equivalent to 6.022 times 10 to the 23rd. So you guys work on this one. Given you have 18.4 grams of silver. No, not grams. We are so not even there yet. Let's go with 18.4 moles of silver. I want you to find number of silver atoms. I'll give you 2 minutes for that. The setup is really the exact same as the last one we did. All right, so looking at this one, we're looking, trying to flip between moles and atoms. So we need to use Avogadro's number. So I just kind of like to write my conversion factors. So 1 mole, and I'm going to put it as 1 mole of silver. Sometimes people get in the habit of just writing 1 mole and they don't give it like a value. Give it like its individual element or molecule, because you're going to have moles of different things later on. So 1 mole of this is equivalent to 6.022 times 10 to the 23rd silver atoms. So we start with our given information, which is this thing right here, 18.4 moles of silver. I'm going to use the conversion factor and set it up in such a way that the mole will cancel. So the 1 mole of silver will go on the bottom, and the 6.022 times 10 to the 23rd silver atoms will go on top. The moles of silver will cancel, and you'll be left with units of just silver atoms. I'm just going to plug it into your calculator. 4. And I get 1.11 times 10 to the 25th silver atoms. Oh, hold on 1 second. No, I think that's right. Yeah, that's right. So any questions on this going from moles to atoms? Let's go the other direction, okay? I'm gonna give you atoms and I want you to come up with moles. So given that you have 3.62 times 10 to the 24th sulfur atoms, I want you to find moles of sulfur. Okay, the conversion factor is the same, but you set it up slightly differently. So I'll give you 2 minutes. Okay, so how does this one differ? We're still using that relationship of Avogadro's number. 1 mole of sulfur is equivalent to 6.022 times 10 to the 23rd sulfur atoms. We're also talking about sulfur, but the conversion is the same. When I set it up though, I'm starting with atoms. So 3.62 times 10 to the 24th sulfur atoms. That means when I convert, I need to put the sulfur atoms on the bottom. So I'm going to put that 6.022 times 10 to the 23rd sulfur atoms on the bottom, and the 1 mole goes on the top, 1 mole of sulfur up on top. So sulfur atoms will cancel and you'll be left with units of moles. Now, when you're plugging this into your calculator, doesn't matter so much here because everything is up on the top. So it's all multiply, 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 right? Here it matters though, because you're taking this number and you're dividing it by this whole thing, not just 6.022. You're dividing it by 6.022 times 10 to the 23rd. So you need to make sure you either put that in parentheses or you use the EE function on your calculator. So I'm using my cell phone, turn to the side, and the EE function is there. So you're going to plug it in as 3.62 EE to the 24th. You don't want to do EE 10 to the 24th because you'll double up on your exponent. So it's 3.62 EE 24 divided by 6.022 EE 23rd. Okay. So if you want to give it a try that way on your calculator, see if you can get that function to work. If you use the EE function, it's nice because I don't have to like put this in parentheses because it seals those things together. All right, if you're using times 10 to the 23rd, you have to put parentheses around it. So this EE function is taking into the account 10 and the caret to the, that's using all of that in there. So try it out. I'll give you a minute or so to try it out and see if you can get the same answer. Oh, I didn't even give you the answer. The answer 6.01, just 6.01 moles of sulfur. If you didn't get that, if you're like, ooh, I got like a really big number with a huge exponent, what probably happened is you plugged this into your calculator, you did this, you hit divided by 6.02 and then times 10 to the 23rd, and you didn't like parenthesis it out. So the calculator is going to do what you tell it to do. It's going to take this, it's going to divide it by this first thing, and then it's going to multiply it by the second thing. So go ahead and recalculate or try it with the EE function. And if you have any questions on the calculator, ask me right now, and I'll do my best. Everyone has a little bit of a different calculator, but I'll try and work with you. So I want to make sure you're getting the right answer. Okay, any questions with calculator function? Feeling pretty good there. Okay, we'll do one more. This same thing applies if you have a molecule. So given that we have 8.2 moles of water, and I want you to find water molecules. I will give you 2 minutes for that. Okay, so Andrea, let's see. You're getting 5.57. Let me try and double check my calculation here that I didn't do it incorrectly. 3.62 24 divided by 6.022 23. Yeah, I'm still getting 6.1. Can you, Andrea, can you try again? Make sure you're really watching 3.62 EE24 divided by 6.022 EE23, because I'm getting 6.01.
After the EE, are you doing the caret 24 for the exponent? Just 24.
Just 24, yeah. So the caret gets included in the EE. That is the exponent as well. Okay, that's what it's telling your calculator to do. Andrea, you try it again. Before we move on to this water one. Got it. Okay, cool. So for this one, very similar to the other ones, except we're dealing with molecules, but it still applies. So 8.2 moles of water. And we're going to do 1 mole of water will yield 6.022 times 10 to the 23rd water molecules. So we want moles of water to cancel. I always check and make sure things are canceling. So I know I did it right. 8.2 times the 6.022, 23. And we get 4.9 times 10 to the 24th water molecules. Well, that's how you convert between moles and atoms or moles and molecules. And actually, I want to go back to that little flow chart we had made and add to it. No, more. Hold on one sec. I want to erase the flow chart. So we have moles to atoms. We also can do moles. This is moles of element to atoms, and this is, we'll do moles of compound to molecules of compound. Follows the same thing as this does. That's why I'm putting them sort of next to each other. We use Avo's number. That's what we just did with the water molecule. Okay, so you can go back and forth using Avogadro's number between either moles of the compound and molecules of the compound, or moles of the element and atoms of the element. So when we're talking about a mole of one thing and a mole of another thing, they don't necessarily have the same weight. Just like a dozen large nails and a dozen small nails don't weigh the same thing. Which one of these would weigh more? The dozen large nails would weigh more. So when looking at a mole of sulfur or a mole of carbon, they have two different masses. The mole of sulfur, the mass of 1 mole of sulfur is 32.06 grams. The mole of carbon mass for 1 mole of it is 12.01 grams. Do those numbers sound familiar at all? They should, because they are the atomic masses on the periodic chart. So go ahead and grab your periodic chart. Go to sulfur, which is number 16. And the number, the decimal number at the bottom is the mass. And remember, the mass is the average of all the isotopes together. What is the mass of sulfur? 32.06. How much does 1 mole of sulfur weigh? 32.06. So that number is not just the atomic mass. Sometimes that number is referred to as the molar mass, the amount of mass in every 1 mole. Carbon has a molar mass of 12.01, right? We look on the chart, what's right underneath your C? 12.01. So how much does 1 mole of zinc weigh? You don't have to come up with it out of thin air. You've got your periodic chart, you can go take a peek. 1 mole of zinc should weigh about 65.39 moles, or 39 grams. Don't use the 30. The 30 is talking about the number of protons. That's atomic number. We use the atomic mass. How much does 1 mole of barium weigh? Find it on your periodic chart. Find that decimal number. It should be about 137.33 grams in every 1 mole. Barium is number 56. So the molar mass of any element is the mass of 1 mole of those atoms. And we can write it in a couple different ways. So for copper, for instance, the atomic mass of copper is 63.55 AMU. 1 mole of copper atoms has a mass of 63.55 grams, or the molar mass of copper is 63.55 grams per mole. Anytime we have a double unit like this, it's a conversion factor. We could say 63.55 grams of copper is equivalent to 1 mole of copper. All right, now we can convert between moles and grams, or grams and moles, because we have the molar mass. This is specific and unique to whatever you're talking about. Remember when we were going from moles to atoms, it didn't really matter what the material was because it's always that Avogadro's number. But if we're going from grams into moles, we have to be very specific about what the material is because it's different for each one. So all of these things are 1 mole, 1 mole of sulfur, 1 mole of carbon, 1 mole of lithium. They all contain 6.022 times 10 to the 23rd atoms of those individual things, but they all have different masses. Why? Well, because sulfur is a way bigger atom than carbon is, and carbon is a bigger atom than lithium is. Lithium's a tiny atom, so we wouldn't expect it to have a lot of mass for the same amount. The lighter the atom, the less the mass is in every 1 mole. What is the lightest molar mass on the periodic chart? Hydrogen. Hydrogen has a molar mass of 1.01 grams in every 1 mole, much lighter than the other ones. So let's add to our flow chart over here. Let's put grams of element. So you can go from grams of element into moles of the element or vice versa using the molar mass. And if you want to add here, you can put in parentheses off the periodic chart. Okay, so the molar mass, you're not going to you're not going to come up with it out of thin air. We'll do one together and then I'll have you guys do one. So let's say that we're given that we have 6.24 moles of potassium. And I want to find grams of potassium. So looking at our flow chart here, we're starting at moles and we want to go into grams. So I recommend having this written out because it kind of tells you what to do. So if we're starting at moles and we want to go to grams, we need the molar mass. So let's write the molar mass of potassium. We have that there are for every 1 mole of potassium, we get 39.10 grams of potassium. You guys see where that number comes from off the periodic chart? All right, so now when setting it up, I'm going to start with my given information. 6.24 moles of potassium. And we know that for every 1 mole of potassium, we get 39.10 grams of potassium. Some people will memorize it like, oh, if I'm going from moles into grams, I need to multiply by the molar mass. If I'm going from grams to moles, I have to divide by the molar mass. I don't think of it like that. I just think of it as how do I get the units to cancel and then let it tell me what to do. So I put the mole on the bottom here, multiply it on the top. The 1 always goes with the mole. The value always goes with the gram. So we've got our 6.24 times 39.10. I'm going to go with 2 sig figs here, or 3 sig figs rather, and I get 244 grams of potassium. There's 244 grams of potassium and 6.24 moles of potassium. Questions for that? And where those numbers came from, how I set it up. Okay, I'm going to have you do this one. Given you have 136.2 grams of zircon, and I want you to find the moles of zircon. I'll give you 3-4 minutes for that. Okay, so for this one, we need to talk about the relationship of zircon, the molar mass. 1 mole of zircon is equivalent to 91.22 grams of zircon. Start with our given, 136.2 grams of zircon. I'm going to put the mass on the bottom and the mole on the top. 91.22 grams of zircon on the bottom for every 1 mole of zircon on the top. The grams will cancel. So in this case, you divide by its molar mass. Again, I don't think of it as multiplying and dividing. I just put it into my dimensional analysis and do what it tells me to do. 91.22. We get 1.493 moles of zircon. So we're going to do a double problem because how often are you given moles like in a lab setting? You're not. You're usually given grams in a lab setting. And then I would want to know maybe the number of atoms. So in this flow chart here, you could be given grams over here, and I want you to find atoms, and you have to do 2 steps. Or I could give you atoms, and you want to find grams, and you have to go back 2 steps. So the mole sometimes is called like the crossroads in chemistry calculations, because you always have to go through moles. There's no direct way to go from grams to atoms or atoms to grams. You have to cut through moles. So we'll do a 2-step problem here. Let's say that we're given, and I'm going to have you just jump right into it because you've already done each of the components. How many atoms are in a 0.74 gram diamond? And when I say diamond, I'm talking about carbon, because diamonds are made out of pure carbon. That's why they can take your old pup and compress it down into an artificial diamond. People do that. They take grandma and they pressurize into a diamond and wear her around her necklace. It's very strange. Yeah, you could take the carbon material from your loved ones and make artificial diamonds. I've never done that. But maybe somebody knows someone out there who has. But anyway, okay, do the calculation. So we're going from grams. I'll get you started. You're going from grams. Given is 0.74 grams. You're trying to find atoms. I'll give you 5 minutes for that. Give you all just another 30 seconds or so. Okay, so this is a two-step problem. We're going from grams of carbon. We got to get that first into moles of carbon. And then from moles of carbon, we'll get it into atoms of carbon. So 2 steps. The first thing, going from grams to moles. Right here is to use the molar mass. 1 mole of carbon is 12.01 grams of carbon. And then this here, we'd use Avo's number, which is the same no matter what we're dealing with. So we start with our given 0.74 grams of carbon. I'm going to use the molar mass, and I'm going to put the mole on top, put the gram on the bottom. From there, we're going to convert from moles into atoms. So 1 mole of carbon will yield 6.022 times 10 to the 23rd carbon atoms. Grams cancel and moles cancel. You should be left with just carbon atoms. You get 3.7 times 10 to the 22nd carbon atoms. Any questions on that? Some people will say, how many decimals do I need to use for the molar mass? Right, can I just use 12 instead of 12.01? I'd say use as many as you can tolerate. Like for oxygen, oxygen is 15.999 something. I just use 16. Okay, you'll see me just use 16 for oxygen. But if, you know, like for instance, chlorine, 35.45. You're definitely not going to want to round that to 35. You're going to want to use the decimals. So use 2, 3 if you can. Okay, are we good with this? Or do you want to do one going in the other direction? Or do you feel like you've got it? James says he's good. If anybody else?
I have a question.
Yeah. What's up, Rachel?
So I'm confusing myself when you get like 3.7 times 10 to the 22nd. Where are you getting the 10 to the 22nd?
Where am I getting it?
Yeah.
Like, do you see it on your calculator? Do you see an E22?
I'm using the Texas Instrument calculator, so no.
So when you plug this into your calculator, are you just getting 3.7?
Hold on, let me try it again. Okay, I see it now. Never mind.
You got it?
Yeah.
Okay.
Sorry.
Yeah, no worries. Anybody else? Right. So what happens if we want to do a situation where we go from grams of a compound into moles of a compound? Well, in that case, we need to calculate the molar mass for the compound. And the molar mass for the compound is the mass of 1 mole of the molecules or formula units of that compound. So when you calculate the molar mass, you're just going to add up all the individual components. I feel like just easier to show you an example. So right here, let's add another limb and put grams of compound. And this is, we do this by doing the molar mass of compound. Now, how do we get the molar mass of the compound? Well, let's do water. That's a simple one. So, what is the molar mass of H2O? Well, let's take inventory of what we have. We have hydrogen and we have oxygen. What is the molar mass of hydrogen? It's 1.01. And how many of them do I have? I have 2 of them, right? So I'm going to multiply this thing by 2 to give me 2.02. Oxygen, I have 16 times 1 for an overall value of 16. And I'm just going to add those 2 together to give me 18.02. So 18.02 grams of H2O in every 1 mole of H2O. You just take whatever's there, multiply it by its subscript, and add them together. So I want you to tell me, I want you to calculate molar mass of Al2O3 and the molar mass of FeSO4 2. Give you 4 or 5 minutes for that. Okay, so molar mass of aluminum oxide, Al2 O3. Aluminum has a mass of 26.98. And we're going to multiply that by 2. And we've got oxygen, which is 16. We're going to multiply that by 3. You get what, 53.96, 48. Add those together. 101.96 grams per mole. This one over here, we've got 3 things. We've got iron, sulfur, and oxygen. Iron is 55.85. Sulfur is 32.06. We're going to multiply that by 2. This gets multiplied by 1. And then oxygen, which is 16, and that's going to get multiplied by 8. 4 inside, 2 outside. So we get what, 55.85, 32.06 times 2 is 64.12. And 16 times the 8, 128. We get 247.97 grams per mole. So when you're solving for problems with a compound, if you have to use the molar mass, you got to do an extra step, right? You got to add it together. So let's do a problem. How many molecules of, let's see, how many molecules of MgOH2 are in 56.2 grams? I'll give you a couple minutes for that. Okay, so for this problem, we're dealing with MgOH2, and we're going to go from grams of MgOH2 into moles of MgOH2 because we, moles is our crossroads. And then from there, we'll go into molecules of MgOH2. So write our grams, 56.2 grams, the MgOH2. We use the molar mass, so 1 mole of MgOH2 should weigh 58.32 grams. 1 magnesium, 2 oxygens, and 2 hydrogens. Then from there, we use Avogadro's number because 1 mole of anything is equal to 6.022 times 10 to the 23rd individual parts or molecules. We get a value of 5.80 times 10 to the 23rd MgOH2 molecules. You guys feeling good with that? With how to flow around those charts, whether it's a compound, it's up here, whether it's a compound or an element. So in the very beginning of class, we were talking about salt and its relationship, or sodium and its relationship to salt. So how do you know how much sodium you have in a given compound of sodium chloride, or how do we relate these two things to each other? The last thing I think we'll talk about for today, and then we'll call it and we'll be good to go, I think, just to meet on Tuesday of next week. All right. So let's look at the clover analogy. So one of these clovers has 3 leaves. All right, one thing can contain multiples of another. All right, so if we were to run a calculation where it says, hey, how many leaves are in 14 clovers? You may be thinking, oh, well, obviously I just multiply it by 3. But if we were to set it up in dimensional analysis using this relationship, we know that for every 1 clover, we get 3 leaves. We take the clovers, multiplied by the leaves, divide by 1 clover, the clover cancels, and we get 42 leaves. Let's look at some other examples. 1 spider has 8 legs. 1 chair has 4 legs. Okay, what does that have to do with chemistry? Not a whole bunch, but this is important. 1 water molecule contains 2 hydrogen atoms. Okay, so 1 molecule can contain multiples of another thing. If we look at CO2, CO2 contains 2 oxygen atoms, which we could say is also related to 2 dozen oxygen atoms for every 1 dozen CO2 molecules, or we can extrapolate that, and this is really where we're going to want to go, is that 1 mole of CO2 contains 2 moles of oxygen. And sometimes people will say, well, how can 1 mole of something have 2 moles of it? Well, this is 1 mole of a really big thing or a bigger thing. This is 2 moles of a smaller thing, right? This is a mole of a big molecule. This is a mole of just an element. So our formulas, every single formula we have has a built-in relationship. That's true for any formula. Let's go back over here to those guys we were calculating the molar mass for. Al2O3 and Fe2SO4. So some of the relationships we can find there. One mole of Al2, I don't know why I want to call it S, Al2O3 contains or has how many moles of aluminum? Well, look at the subscript, 2. So we get 2 moles of aluminum. We also know that for every 1 mole of Al2O3, we get 3 moles of oxygen. We also know for this specific compound, hold on one sec. For this specific compound, 2 moles of aluminum will combine with 3 moles of oxygen to give us the product. So those are all the different relationships we have within this compound. We look at the other compound. Actually, I want you to look at the other compound. So FeSO4, 2. I want you to tell me all the different possible relationships you can come up with for this, because each of these relationships is a conversion factor. I'll give you 2 minutes for that. Okay, so I'm just going to chain them all together in one long sort of relationship. So 1 mole of FeSO4, 2 will relate to 1 mole of iron. Right, there's only 1 iron in there. I'm just going to keep them all chained. 2 moles of sulfur. And then 8 moles of oxygen. And you can sort of pick and choose what you want to use from this relationship depending on the problem. So let's say we're given that we have 11.4 moles of FeSO4, SO42, and I want to find moles of oxygen. I just want to know how many moles of oxygen it is. Well, get this stuff on. Well, if we know moles of the compound, that's what we're talking about, and we want to find moles of oxygen, I'm just going to use these two relationships. What are these guys for? I don't need them in this given problem, so I can sort of ignore them. I'm just going to look at these two. So we know that for every 1 mole of FeSO42, I'll get 8 moles of oxygen. Here's moles of compound, here's moles of oxygen. Let's do a conversion factor. 11.4 moles of the FeSO42. We'll put the 8 moles of oxygen on top because I want to go towards oxygen. I want to get rid of this compound, 1 mole of the FeSO42. These cancel, and it looks like all we're going to do is take our initial value and multiply it by 8 because we get 8 oxygens in every one of those compound packets. We'll get 91.2 moles of oxygen. This works for any compound. Every compound is a recipe. This recipe is a molar relationship. I think that's important for people to know. It's a relationship between the moles of each thing. It's not a mass relationship, not, write it in red. Not a mass relationship, which sometimes people will get in the habit of saying, oh, well, when I look at this, this is like 1 gram of sulfur for 8 grams of oxygen, right? No, it's a mole relationship. It's 2 moles of sulfur for every 8 moles of oxygen, not a mass relationship. So I think the slides go over one here and we can look at it real quick and then we'll call it for today. So converting between moles of a compound and moles of a constituent element. It says find the number of moles of oxygen if you have 1.7 moles of calcium carbonate. When we know the calcium carbonate amount, we want to find the oxygen amount. We need the relationship between those two, and we know that 3 moles of oxygen come from 1 mole of this. Why do we know that it's 3? Because the subscript tells us it's 3, right? That's where those numbers are coming from. If it had asked for calcium or carbon, it would be a 1-to-1 ratio. But for this one, it's a 1-to-3 ratio. So we simply plug that in, start with our given information, put the compound on the bottom and what we're going towards on the top, cancel, and we get 5.1 moles of oxygen contained within 1.7 moles of calcium carbonate. Now again, how often are we given moles in real life? Not ever. We don't have scales that give us information in moles. They give it to us in grams. So usually we need to go from grams into moles and then moles into grams. And that we will start this flow chart here. We will do next week. Okay. So thanks for sticking with me today. Lots of information. We will get through this chapter hopefully fully on Thursday or Tuesday. We don't have a whole lot left. And then Thursday of next week, we'll probably not meet. We'll break unless something crazy happens. So have an awesome weekend. Have a good 4th of July. Do not forget to take your test at some point, Sunday through Tuesday. Yeah, if you have any other questions, stay around. Anything general, throw out there. Anything personal, wait until we can get some privacy.